This is lesson 1 of unit 13, and in this unit we will talk about solutions. Solutions are essentially a mixture of solids and liquids and gases. Well, previously we talked about these individually. In this chapter we're going to put them all together and it'll make a solution. So let's go ahead and define what a solution is, and then we'll give you some examples. A solution is a homogeneous mixture of two or more substances. Now, homogeneous, recall, means it's a thorough mixture. It's perfectly mixed. So this is in contrast to a heterogeneous mixture. Homogeneous means the two compounds or chemicals are completely mixed, as you see in the case on the right. Heterogeneous would mean that they're not perfectly mixed. They're together, but they're not perfectly mixed. So a solution, by definition, has to be homogeneous. So what you see here on the right side is a simple example. If you put some salt or some sugar in water and you mix it up, eventually it'll be mixed up very well and you get yourself a solution. That's kind of the idea. Now, a solution has two parts. The first part of a solution is the solute. This is what's being dissolved, and the solvent is what's doing the dissolving. So in the case of this is sugar and water, then the sugar would be the solute because it is what's being dissolved. The water then is the solvent, what's doing the dissolving. And very often water is the universal solvent. Actually, water is called in chemistry universal solvent. And because water can dissolve a lot of things. Now, not everything obviously, but water can dissolve most of the things that we care about. In fact, our bodies are essentially bags of water. They dissolve many, many chemicals that our body uses. Now, the way to remember this is here it says there's always more solvent and less solute. And if you take a look at the word solute, if you count the letters, 1, 2, 3, 4, 5, 6, we have 6 letters in the word solute. 1, 2, 3, 4, 5, 6, 7 letters is solvent. The longer word is the one that you have more of. There's more solvent and less solute, is the idea. So here are a few examples of solutions. Solutions don't always have to be a solid in a liquid. Here we have some solutions that are two solids. So for example, this is brass, and brass is copper mixed with zinc, and it's a solution essentially, and it's a perfect mixture. So you have two solids, that could be a solution. Here you have yourself a gas essentially dissolved in a liquid. A soda, the thing that makes it fizzy is you have a gas in a liquid. And there's also a bunch of other solids dissolved in the liquid, but primarily you get the gas in the liquid. That's what makes it soda. And you got many other examples. Here it says that these are alloys. So here's a white gold alloy. Here's another alloy. And I don't know who wears this or what happens to it next. But we'll show you some examples of these as we roll along. So now solutions can either be electrolytes or non-electrolytes. So when you dissolve something and it conducts electricity in water, many solutions do, it's called an electrolyte. And this is done by your ionic compounds, like sodium chloride. Remember, this is table salt. Now, an ionic compound, recall, has ions in it. And it has ions in it because it has a metal and a non-metal for the most part. So you have a positive ion, that sodium, and then you have a negative ion, chlorine, and when you throw these into a solution, they split up. So here is a picture of it. And the negative and positive ions split up. This is called dissociation. They dissociate, they split apart, and allow electricity to flow through it, essentially. So electrons can flow through this now. Whereas a non-electrolyte does not conduct electricity, and this is usually your covalent compounds, like sugar. And what you see here is that sugar is dissolved, and so it's swimming around. As you'll see in a minute, dissolving means it's swimming around in the solution, but it does not conduct electricity because it does not produce ions, because it is covalent and not ionic. So let's take a closer look at the solution process. So here it says, how can you make a solid dissolve faster? Before we discuss that, let's take a look at the actual solution process. So here you have an example of sodium chloride of a salt. Here's sodium chloride. And the big atoms are actually the chlorines, the negatives. The small atoms are the sodiums. These are actually ions. Now what happens is water comes up. If you throw a crystal of salt, this would be like a little crystal. If you throw that into water, the water molecules will quickly run up to it and start bonding with the ions. Here you see a water molecule, the negative side of a water molecule, which is represented by this red oxygen, is attracted to the positive ion. And they attract each other, and then they carry each other away. So the water molecules run up, bond, and then here you see 3 water molecules carrying away a little sodium ion. You see the same thing here. You see 4 water molecules dissolving and carrying away a chloride ion, and the positives of the water molecules are actually attracted to the negative of the chloride. So this is what making a solution means. There are bonds being formed. So, and these are actually intermolecular bonds, you can say. These bonds are actually being formed between the particles. So there are 3 things you can do to speed this process up. Number 1, you can increase the surface area. And increasing the surface area just means you would cut it into smaller pieces. And what this does is essentially, if you cut this up, then you're allowing water molecules then to access the middle of the salt. Remember, this is just a crystal of salt. Originally, the water molecules can only come from the outside and dissolve and grab salt particles and take them away. But if you split it, now they can come on the inside. If you split it into 1,000, 1,000,000 little pieces, then this can happen much, much faster. The other thing you can do is you can agitate the solution, which means just stirring it or shaking it. This moves the water molecules around faster. You're helping to move the molecules around, and they dissolve it faster. You can also add heat, which means you're increasing the kinetic energy, increasing the energy of motion. Move faster. And so if they move faster, then they can find the particles faster and dissolve them faster, which makes sense. Let's give some more definitions between a saturated and an unsaturated solution. So here, a saturated solution is a solution that has the maximum amount of dissolved solute. The word saturated actually, you can say, means full of something. So if you have a saturated sponge, it's full of water. A saturated solution is full of salt. So any more salt you add will fall to the bottom because it's full. Whereas an unsaturated solution has less than it can hold. So if you have yourself a beaker, and in that beaker you have a solution, if you add more salt to the beaker, add more salt, more dissolves. That's because it's not full yet. If you add more salt, more dissolves. Eventually, when you add more and it falls to the bottom, that's when you have yourself a saturated solution. Now there is a type of solution called a supersaturated solution. This is a strange one. This one contains more dissolved solute than the solvent can handle. So what we're saying is you can actually dissolve more sugar in water than you can dissolve. This sounds strange, but the way you do it is you first heat up the solution. So here you have a solution. You would apply some heat to it, heat it up, and a hot temperature can actually dissolve more salt. So you can get many more particles of salt dissolved at a higher temperature than you could at a lower temperature. So what you do then is after you're done dissolving more, then you cool it back down. And when you cool it, what you'll get is you'll get yourself a solution that's supersaturated, that can have more dissolved particles than it can handle after you cool it back down. Now this actually is an unstable solution, and the particles could precipitate out, could salt out, but it will be supersaturated for the time being. If you cover it, it'll actually remain supersaturated for a long while. And this is actually how rock candy is made. This process is used to make rock candy. If you know anything about rock candy, essentially this is just sugar crystals that have been put together. The way you make it is you take your sugar and you dissolve the sugar in as much water as you can by heating it up. or I'm sorry, you dissolve as much sugar as you can in hot water. Then you would pour this off the liquid into a solution, or into a container. You can put it in one of these jars. And then you would suspend something in the jar, like a string. You can do a piece of wood, and leave it for a number of days. And as the water slowly evaporates, the sugars crystallize. The crystals begin forming. The sugar comes out of the supersaturated solution and forms on the string. And you can add some food coloring, some flavoring, and that's how you get yourself a supersaturated, or a rock candy from a supersaturated solution. Now, we'll finish up the video by discussing why solute and solid particles mix or don't mix. So you know famously that oil and water, this is down here, it's water-based. I know there's a bunch of other chemicals, but they do not mix. They're not able to mix. And the reason for this is a rule in chemistry that says like dissolves like. So similar molecules dissolve similar molecules. That's what we mean. And by similar molecules, we're either polar or we're nonpolar. So polar will dissolve polar, nonpolar, nonpolar. In this case, oil is a nonpolar molecule. It's equal everywhere on both sides. Water is a polar molecule. It's unequal. There's a negative side, there's a positive side. This is what makes it polar. So that's why these two will not dissolve in one another. Now, there's a famous molecule that can actually do both, that has both a polar and a nonpolar side. And that famous molecule is soap. Very powerful, very famous. A soap molecule is represented down here, and it has a polar end. This is an end that has a positive and a negative side on it. And it has a nonpolar end, an end that is equal. So this end right here can dissolve oils or fats, and this end here can dissolve water-based things like dirt and other things. So actually soap has been made, engineered, and it's been known about for a very long time in history as a molecule that can do both. And finally, this definition of miscible. Miscible means that substances completely dissolve in one another in any proportion. So this is actually more than soluble. Soluble means you can dissolve it, soluble, but miscible means any amount in any amount. So for example, you can do it 50-50, you can put 50% water, 50% of your the other compound. You can do 10-90, you can do 7-30, you can 70-30, you can do any proportion. This is called miscible. Very famous example is alcohol and water. So here's water, and here's alcohol. This is ethanol, an alcohol called ethanol. And any amount of ethanol can dissolve in any amount of water. Now this is due to hydrogen bonding. Because the two chemicals have a similar intermolecular force. In fact, right here you see the OH, the hydrogen bonding. They can then attract each other and bond with one another. And that's why many things are miscible, because very often things that are miscible have hydrogen bonding or very similar intermolecular forces ruling them. Let's go ahead and finish up with this example. And the example asks, which of the following compounds will dissolve in one another? The way we'll determine this is by asking which are polar and which are nonpolar. So let's go through here and mark them as polar or nonpolar. If you take a look at this molecule, we ask ourselves, is it equally dispersed? It is not. We have a difference on the top versus the bottom and the right. So this is a polar molecule. The molecule on the right is actually nonpolar because it is equally dispersed. The molecule doesn't have a difference on one side versus another. This molecule here is also nonpolar. It's all the same throughout, whereas water is famously polar. So we can then say that these two molecules will mix with each other. Water will actually mix with ammonia. And we can say that these two molecules will mix with each other. And in any proportion, actually. These will be miscible. Simple as that. Not too bad. Go ahead and try an example problem of your own. Here it is, example 1. And we'll do some more of this in class.